for manifolds.
Yeah. Well, thank you for coming. So I'm going to tell you about some connection between algebraic surfaces and low-dimensional topology and basic construction of some manifolds that appear in both sides. So the first part that I'm going to explain is going to be over C. Then I'm going to explain the topological part over R, and then I'm going to try to make the connection between the two. So these homology planes are affine smooth surfaces that have the same integer homology of the complex plane. So we basically call a homology plane. And they appear for the first time in a paper of Kirby-Ramanujam around 71, where he was considering something called cancellation problem. So you have some algebraic variety, you multiply by C, and you ask if it's isomorphic to C3 in this case. Similar to the problem that Leonardo was considering. And Ramanujam writes that at the time it was believed that if you have an affine smooth contractible surface, it was believed that it was C2. So he showed a counterexample of that. And the counterexample is the following. So you have to consider two curves in P2. And one of them is going to be a smooth conic that I denote by C1. So this is green line here. And the other one is going to be a cuspid and cubic. So it's this C2 here. And they need to be intersecting as follows. So you will have one transverse point here at P, and the other one with intersection with multiplicity 5 at Q. So that thing exists. You can even have explicit equations for that, but believe me that exists. So if you have this, we can make the blow up at P, and you can consider the strict transform C1 tilde and C2 tilde. I have the green line, the green curve now here, now the blue curve here, and I've separated them. And the Ramanujam surface is in this blow up. You remove the strict transform of C1 and C2. Okay. And this is the Ramanujam surface. Okay, so you remove these two strict transforms in the blow up, and that's going for me to be X. So what are the properties of this? We have that X is going to be contractible, but X is not algebraically isomorphic to C2 or analytically isomorphic to C2. One reason of that I'm going to explain later is that X is of low general type, whatever that means. But you can also say that its fundamental group at infinity is non-trivial. So I won't define what this means. But let me say that Ramanujam also gave some characterization of C2 as not only a surface that is contractible, but it's also simply connected at infinity. Whatever that is. Okay, so now this Ramanujam surface can be used to give exotic algebraic in analytic structures on Cn for n bigger than 3. And for this, we use this cancellations theorem that I was telling you. So in the algebraic setting, this is due to Itaka and Fujita, 77. In the analytic setting, this is due to Seidenberg. And it can also be used to construct symplectic exotic structures on C2 to the n, basically taking powers of x times x times x. But we don't have cancellation theorems in this symplectic world. They use basically symplectic homology. In the cusp, you will have some Lagrangian that they call non-displaceable Lagrangian that you cannot move. and that will give an element of symplectical homology, and so it's non-trivially symplectically as well. Okay, so now something that will be useful for us will be this something called the dual graph. And to associate a homology plane, a dual graph, we will do the following. We can write x as x bar minus d, where x bar is a smooth projective variety, and d is a simple normal crossing divisor. What is the meaning of that? It means that locally this divisor looks like a line or an intersection of two lines like this. And then we can make the minimal embedded resolution of this curve that we were removing in the blow-up of P2. And to every line, we can associate a point, and whenever two lines intersect, we associate an edge. And we can weight this graph with the self-intersection number of the lines. And in this way, we associate a graph to this divisor. Okay. So now, let me go a little bit into the classification of these homology planes. And for this, we need some invariant. So I will say some words that if you don't understand, you just have to keep in mind that we have some invariant. I mean, this is for people that are not algebraic geometers. But if you know this is, use the collider dimension, the logarithmic collider dimension. And for this, we have a smooth quasi-projective surface. We choose a simple normal crossing compactification. And then this invariant can take the value minus infinity, 0, 1, or 2 for this quasi-projective surface. So how it is defined? So, well, it is defined in the following way. You need to take the dimension of the space of sections of the multiples of kx bar plus d. And this will be bounded between some two numbers with some positive constant alpha and beta here, and n to the power this invariant, whatever that means. So we have to take m sufficiently large and divisible. Okay, so we have some invariant that can tell us something about the complexity of the quasi-projective surface, and we will apply this for homology planes. So it was known by Fujita that if we have a homology plane and the dimension is minus infinity, then actually x is C2. Also, Fujita showed that we cannot have homology planes with logarithmic collider dimension 0. And so we have only left 2, 1 and 2. And those homology planes with logarithmic collider dimension 1, they are completely classified by Gurja and Mijanishi in '88, and they arise in the following way. So you have something called a quasi-pencil of lines in P2. So it's basically a bunch of lines passing through one point, but then you put another line that is in general position. Then you have to blow up points here, points in the line L1 until Ln minus 1, intersecting Ln plus 1. So basically those points. But you will have a number of choices to make. They are basically codified by n2 tuples, and then this will tell you how you should make the blow up here. And at the end of the day, you will have a -1 curve, and you don't remove that -1 curve. You remove everything but that -1 curve. That's very similar to the Ramanujam construction. In the Ramanujam construction, we blow up and we remove the strip transform, but not the exceptional divisor. I don't want to enter into details, but so we were looking some Calabi-Yau surfaces, and in the language of that, we have to make some corner blow-ups and some interior blow-up here. So that's the way you can get the homology planes with collider dimension 1. And let me say that if this invariant logarithmic collider dimension is 2, we say that x is of log general type. So this is the case for the Ramanujam surface that I was telling you. If you compute this invariant, that's going to be 2. And there exists a conjectural complete classification of homology planes of logarithmic general type. So they are actually pretty rigid. They have a lot of properties that conjecturally classifies them. So let me go for the conjectures. So if you have a homology plane of low general type and you consider a minimal simple normal crossing compactification, we have this conjecture of Tom, Dick, and Petri that says that every homology plane arises from finitely many configurations of lines and conics on P2. So this homology plane that I showed you is a configuration of lines, but we can also have conics. The Coras conjecture tells us that the automorphism group of X has at most 6 elements. So it's of low general type, so it's finite, but you have a bound here. And then the Flener-Seidenberg conjecture tells us that this HI of the logarithmic tangent bundle, so you consider the tangent bundle and you twist it with this minus log D. Those are the vector fields that preserve the divisor D. Then this should vanish. I'm not sure if this should be extremely bigger than 0 here, or I bigger than 0. And then we have something called Falca negativity conjecture that is going to be the really important for the next theorem. And it's some conjecture about the logarithmic Odero dimension of this pair. So you consider chi of x bar plus 1 over 2d, and this should be minus infinity. I'm going to tell you what is.
Just a question, like there's two conjectures, two first, like about the finitely many configurations and the order of the automorphism, they have to be compared somehow, like you have so many configurations as the order of the automorphism group, or is expected to be higher, the possible configurations?
I don't think they are related, because the first one is telling you, like for example here you have only one configuration, right? Mm-hmm. But you can have infinitely many homology planes arising from this configuration. Mm-hmm. So it really depends on the numerical condition that you put here. It will give you a different homology plane. And so different conditions can give you different automorphisms. So it's not really related to the automorphisms of the original variety, mm-hmm. but it's related to the final. I mean, maybe another question would be, we can relate the automorphisms here. That I don't know.
Thank you.
And so the theorem of Tomasz Pelka, published last year, is that if you assume this Falca negativity conjecture, then all the other conjectures are true. So he classified all the homology planes, all the possible configuration of all line and conics in P2, and it can give rise to homology planes. So that's the meaning of they are conjecturally classified. So he checked also the automorphism, and he checked also the vanishing of the cohomology of this logarithmic tangent bundle. So what's the idea? The idea is that if you assume this conjecture, this Falca negativity conjecture, you can obtain a minimal model of this pair, and that's going to be something called log modic fiber space, and that can be fiber over a curve or over a point, and you can start making classification there. But okay, that's not really the point today. So that ends the part of algebraic geometry. Let me stop for questions here before passing to Mazur manifolds. Any question? So let me go to the topological part. Let me recall you that if you have a smooth n-dimensional manifold with boundary, you can attach some handles. So you're attaching basically topological cells, and you make them of the right dimension to continue have an n-dimensional manifold. And so an n-dimensional k handle is a copy of this product of disk, dk times dn minus k, attached to the boundary of x along the boundary of the first part times the second, and we use an embedding of this manifold here. So let me give you a very trivial example. Is when you glue a zero handle to this, you basically take the boundary of D1, those are 2 points, so you select 2 points, and then you can glue a zero handle out of this. So now, a less trivial example of this is that you can glue a 2 handle in the boundary of this. I will glue a 2 handle in the boundary of S1 times B3, and this is given by specifying some knot inside the boundary of here. So we can choose some non-trivial knot here like this, and then you can glue a 2 handle out of this. You can think of this as the boundary of B2, but it's glued in some twisted way here. So now the definition of a Mazur manifold is as follows. For me, a Mazur manifold is going to be a contractible, compact, 4-dimensional manifold with boundary, which is not diffeomorphic to the standard ball, and such that if you decompose it with this type of handles, it contains 1 zero handle, 1 1 handle, and 1 2 handle. So in some sense, they have a very basic, a very simple handle decomposition. And well, an example that I can give of this is that the 4 manifold obtained by gluing this 2 handle here is a Mazur manifold, and this is the example given by Mazur in 61. So once again, if you glue these 2 handles in this way, you will obtain a 4 manifold that is contractible and compact. So it's close to the homology planes that we were talking at the beginning. They are also 4 manifolds, and they are contractible.
Do you know if it is like a handle decomposition is somehow like a good invariant for something? I don't really know.
I think they can have cancellations, right? I'm not sure if there's something like a minimal handle decomposition, because you really have some moves that can change them. You can add them and something called Kirby calculus. So I don't know if there is something like minimal. Okay, so that's one way to have these contractible 4 manifolds. But now let me review a construction that is closer to something that Koinaru did. And the first part is going to be really equivalent to the Mazur construction. So we have 3 points here. The first one is you need to consider a disk that is smoothly embedded in B4. Here I consider the trivial embedding. And then you have to consider a tubular neighborhood U of this disk. And if you look at the boundary of this U, this is going to be diffeomorphic to S1 times S2. And so in this boundary, you can make an integral surgery in a knot with some fusion number, with some invariant that you can have this, and such that the 3 manifold obtained is a homology sphere. So I'm really just restating the steps to construct this Mazur manifold, and the way to construct this Mazur manifold was to find some knot here, well chosen knot that will kill the fundamental group when you glue the handle. And so the one point that you need to check is that this boundary here can be seen as a zero surgery. So this procedure was described by Şavk in his paper in 2020, and he generalized this to some construction as follows. So instead of taking this smoothly embedded disk, you can take something called a ribbon disk that I won't define. They can admit some simple self-intersection. And then in the second point, I was telling you that you can do zero surgery in the knot to obtain this. And here we can make zero surgery in a ribbon knot, some generalization of this, and we can admit some future number. This is n bigger than 1. So we end up with some three-dimensional manifold, and we can once again do integral surgery in a knot in this three-dimensional manifold obtained in the second point. And if we obtain a homology sphere, a three-homology sphere in this second surgery, the result of Szavk is that this resulting three manifold bounds a contractible 4 manifold. But this time, this number that we call fusion number here will be relevant, and you will end up with a manifold with 1 0 handle, n plus 1 handle, and n plus 1 2 handles. So we will call this a Poinaru manifold. So basically, at the same time, Mazur and Poinaru discovered this type of contractible surfaces, and we were told later by Luis Funar that those existed. So we called Mazur manifolds all of them, and he was telling, oh, this was introduced by Poinaru as well at the same time. And so we changed the name, and we will call this today a Poinaru manifold. And the example that Szavk, or even himself, Poinaru, constructed was that you can make a zero surgery in something called a square knot, and then one can do a -1 surgery in the three manifold obtained, and you will obtain some homologies here that bound some contractible manifold. And you will obtain something with 1 0 handle, 2 1 handles, and 2 2 handles. Now let me make the connection with algebraic geometry, and it's as follows. When you have a diagram like the one I gave you for the Ramanujam surface, that is the dual graph of a simple normal crossing divisor, you can associate a surgery diagram. So for every point that you have here, you can put a knot, and whenever you have an edge, you can tangle these knots here. And you can decorate also with the self-intersection numbers. And this will give you a surgery diagram for a manifold. And if you do Kirby calculus and you end up with some ribbon knot, as I was telling you in the second construction, you will obtain some Poinaru manifold. This is the extra knot that I was telling you in the part 3 of the construction.
So from the point of view of this decomposition, what the -3, for instance, or -2 really means? Like
in this one?
Yeah. For instance, so like what is this number? Yeah.
This is the framing of the knot. So it's related to some normal bundle and some how twisted is this normal bundle. And
okay.
Okay. Any other question? And so basically the contribution is that Szavk was trying to find plumbing diagrams, let's call of this type of graph, such that when you do Kirby calculus, you end up with some ribbon knots. But I mean, he looked at the Ramanujam dual graph, and he said something like, oh, we can add here, 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 and here, and we obtain something ribbon. And at the end of the day, we can use the classification of the homology planes and try to see if by making Kirby calculus of them, I mean, you have already some graph. You can try to see if those will give you ribbon knots, and that's what we did. We use some of them, and we found that some of them were indeed ribbon knots. So let me make the connection between the Ramanujam surface. So Kirby showed in some unpublished work that this Ramanujam surface is essentially some Mazur manifold. And now let me define what is the boundary of a homology plane, even if it's not precisely the boundary. So when you write a homology plane like this as the complement of a simple normal crossing divisor, you can take a smooth tubular neighborhood of D, of the divisor, and we will call the boundary of this tubular neighborhood the boundary of homology plane. So it's used to make the connection with this Mazur manifold that are compact manifold with boundary. We can think of this delta Ux as the boundary of the homology plane. And X is going to be here the Ramanujam surface. And so he basically obtained this, something similar to the Kirby result. So the boundary of the Ramanujam surface bounds a Poinarou manifold. And the computations are just like, as I told you before, you use the dual graph of the Ramanujam surface, you use this this plumb surgery diagram, and you end up with a knot that is actually this square knot. And you can conclude that this is a Poinarou manifold. So now let me define what we call a Kirby-Ramanujam sphere. And this is basically a three-homology sphere that bounds a homology plane and a Mazur manifold at the same time. So the example is this, the three-homology sphere bounding the Ramanujam surface, that you can have both of these. So I was telling you, Şavk generalized this graph as follows. He added some vertices and edges here, and he increased some weight here. And he showed that this will give you Poinarou manifolds. And so the question was if there are some algebraic surfaces that are homology planes and have as a divisor at infinity, let's call it, the dual graph, something like this. So the answer is yes. We just reviewed the literature. So Seidenberg had constructed some generalizations of the Ramanujam surface, and he constructed something similar to this. So we use his construction, and well, he already knew that those were Poinarou manifolds, so we only conclude that these are also Ramanujam, so they are Kirby-Ramanujam spheres. And we also found more examples. We actually found 3 more infinite families that the dual graphs looks as follows. So something that we call xn, zn, and yn. And so I can tell that xn comes from something of logarithmic codata dimension equal to. And this should be especially important. This comes from something of logarithmic codata dimension 1. This also comes from codata dimension 2. And the particular thing about this is that you end up with the unknot. So if you remember the construction of Mazur, to have a Mazur manifold was equivalent to the knot that you end up with is really the knot, not a ribbon knot, but really and so this will give us really Mazur manifold, and the other 2 will give us a Poinarou manifold. And you have here the decomposition. So this is basically something arising as well as the Ramanujam surface. In the Seidenberg construction, we have some choices, and if you make other choices, you end up with this. and you will end up with the same ribbon knot with the square knot. And the particular curiosity about these homology planes of logarithmic data dimension 1 is that you will end up with a different knot for every end, but you basically end with generalized square knots. So the decomposition in handles is like this. You will have n plus 1 handle for z to the power n, sorry, zn. So when you have this this graph, you can actually describe this graph as something called a splice. When you have these three manifolds, the three manifold is, let's say, you can decompose in simpler pieces that are called ciphered fiber spheres or ciphered fiber homology spheres, and those are S1 bundles over P1 with some twisted fibers along some point. So they're basically an S1 vibration over some Pi1 with orbifolds, P1 with orbifold points.
It's not no conflict.
Which one?
Just like this ciphered are just like indeed the homology spheres, like
yeah, those are compact. So those are three-dimensional. Those are compact, and so the idea is the following: you have some S1 vibration over P1 with some orbifold points, and at some singular fiber you can have some tubular neighborhood.
Okay.
You remove it. You remove it also in another ciphered fiber sphere, and then you glue meridian to longitude. You change and you obtain the boundary of these homology planes, or Mazur manifold, manifold that we have here. And we can decompose this. We can give explicit decomposition in the logarithmic data dimension 1 case. They exist for everyone, but we have not the decomposition for everyone. And so the decomposition is as follows. When you are constructing these homology planes of logarithmic data dimension 1, I told you that those depend on some numerical invariants, A1, B1, AN, BN, and they should satisfy some relation that basically impose the condition that the homology is trivial of H1. And if you blow up this arrangement of lines that I gave you at the beginning of the talk, you will end up with something that looks like this. It stopped. So you will have some weights that will depend on this A1, B1 to AN, BN. You will have some continuous fraction, and the weight of these things will be given by those. But the important thing is that you will have n legs here, and you can basically think that this is the n plus 1 leg that is glued here. So we obtained some result with Şavk about the decomposition of this specific homology sphere, but this actually works for all the homology spheres with logarithmic data dimension 1. You can decompose it as the splice of two ciphered homology spheres, and they depend on some parameters. So the first n are the same, A1 until AN, and the last one is the product of all of them plus 1 or minus 1. And we glue them along this last fiber, the construction that I was telling to Leonardo. We remove some tubular neighborhood and glue longitude to meridian. So this is something the thing that I was telling before. And so let me give you some applications of this. So my idea to work on this is really to have some understanding of the topology of algebraic varieties. So I really want to understand, for example, fundamental groups of quasi-projective surfaces, and in this case, the surface is like rational. So really the fundamental group comes from the boundary. And if you understand how the fundamental group goes inside, well, if you understand the fundamental group of the boundary, you have some chances to know what happens inside. But something more specific is to study representations. I would like to know which representations of the three-dimensional manifold extend to the four-dimensional manifold. And well, this turned out to be really complicated. We will see in a minute. But actually, the first application that we can have of this went in the other direction. So Oğuz found that the splice component of this set N homology sphere that I showed you here, this one, if you can splice it here and you can splice it here, they do not bound contractible manifold. And then using some techniques of die-ham, Stuttering and Truong, one can show that that's not bad. One can show that they actually generate a set infinity Suman in the covariation group. So he can have some applications in the low dimensional topology, and the applications to algebraic geometry are not there yet. So
what's the structure for the manifolds you're considering on this theta 3? Like
so these are homology spheres.
Yeah.
Three-dimensional. And then those are homology.
I see.
So I was telling you about these representation varieties that they parameterize conjugacy classes of SU2 in this case representations, and a result of Savelier from the 98 tells you that if you consider something very similar like to this kind of varieties, if you glue two cipher fiber homology spheres with, let's say, 3 legs, 1, 2, 3, 1, 2, 3, the representation variety can be decomposed as the disjoint union of each of the pieces. And so using this, he can conclude that the instanton homology groups vanish for odd G, odd J. And so I asked him if it would be possible to have something like this for more legs, for more singular fibers, and the computations turn out to be more complicated. So we have the following calculation, that if we consider more than 3 singular fibers, you can decompose the representation variety of each splice component as follows. So you decompose as the representation variety that send the last fiber to some non-trivial element, and you separate from those representations that sends the last element to some trivial element. So you write it like this, and some computations can show that we made with him, that if you consider the splice of 2 cipher fiber spheres of this type along the last fiber, then the representation variety of these glue pieces will have these parts as the joint union, the one that sends the last element to the trivial representation, but they will also have some SU3 fiber bundle over some product. And there are actually more complicated representations coming from ones that are irreducible in some component and that are central in other ones. So it turned out to be really difficult to say what is the whole representation variety in this case. And when we have more than 3 singular fiber, the homology planes turns out to be non-contractible. In this case, you really have some perfect fundamental group, and it's actually pretty simple. You have some vibration to some pi 1 with some singular fibers as well, and it looks like another ciphered homologies here, at least at the level of the fundamental group. So I find it really interesting that even in this very simple case, it's very difficult to say what is the relation between the representation of the boundary and the representations of the 4-dimensional manifold. So I expect that some other invariants can be computed, and my expectation is that we can use somehow the algebraic nature of these homology planes to tell something about some topological invariants that can be defined in this way. Okay, for being Saturday, let me finish here. Thank you for listening.